It is often stated that of all theories proposed in this century, the silliest is quantum theory. In fact, some say that the only thing that quantum theory has going for it is that it is unquestionable correct. Professor Michio Kaku. It's my great privilege to welcome you all to the Space for Women show, Series 30, Future Technologies. Will quantum technologies enable the next giant leap of human evolution? Professor Kaku's quote has reunited us today and inspired us to debate on following questions. Will quantum tech make humanity's next giant leap into the cosmos? Will quantum technologies revolutionize our future? And how can quantum tech be commercialized and create new job opportunities? I'm honored to welcome our esteemed guest, Professor Clarisse Diallo. She's a quantum engineer, and Dr. Yogesh Malhotra, a pioneer in quantum information science and AI. Dr. Sonali Mohapatra, a space quantum technology developer. My name is Thi Hien Nguyen, and I'm a UNOSA Space for Women mentor and host. Without further ado, I also will introduce you to today's co-host, Malak Trabelsi-Loeb, and our esteemed show moderator today is Dr. Alethea Duhon. She's a Chief Technology Officer from the Department of Air Force Chief Modeling and Simulation Office. The floor is all yours, Alethea.
Thank you again. First, I want to say thank you to the Space for Women. It's really an honor to be here today. So thank you so much for the kind invitation. I'm honored to be part of this panel today. We have amongst us the presence of exceptional individuals. As you can tell, we have the renowned experts that are going to be talking about this very interesting topic on quantum technologies and how it enables the next giant leap. So I'm interested to be part of this and hear the dialogue. So without ado, I think I'm going to introduce the first guest, if that's okay. Our first guest is Dr. Yogesh Malhotra. So let me pause for a bit and kind of give you a bio of him, because it's really, really impressive after reading this. I mean, it's amazing. He's the chairman and CEO of a New York-based global venture capital and private equity firm, Global Risk Management Network. He's a CEO, CIO, CTO of global digital ventures, to name a few: global Goldman Sachs, Google, IBM, Harvard Institution, MIT, and it just keeps going on. Dr. Yogi is an industry pioneer in quantum information science and artificial intelligence. He has served as industry expert for MIT Computer Science and AI Lab, and Princeton Quantum Computing presentations sponsored by firms such as Goldman Sachs and Citadel. It's my pleasure to present to you Dr. Yogi. Over to you, Dr. Yogi.
Just turn this off. Hello, greetings from New York. It's a pleasure and delight to be here this morning. Thank you so much for being a part of such an esteemed panel of guests here. And I welcome all of you, the organizers, the hosts, and participants and panelists to this presentation. I'll launch my presentation and share my screen now. Great. This is the starting screen. This is an interactive presentation. That means you have lots of hyperlinks, and you can actually download this from this link I have given to you. And if you want to drill down and be a part of content community building this expertise or what we are doing, you can jump in anywhere. I'll show you a lot of doors here. My inspiration for this presentation is the first woman space shuttle commander, Eileen Collins. In fact, I had the privilege and pleasure of teaching at a couple of institutions, universities, where she studied as a student. And I was building the programs there, teaching the cybersecurity, offensive, defensive, ethical hacking. And I was inspiring my students that sky is not the limit for Eileen and cyberspace is not for us. And the broad background and context for this specific presentation is our engagement going back with institutions and organizations like United Nations, US and world governments, parliaments, cabinets, National Science Foundation, and others, in focusing on world development, survival, and sustainability. For people like Elon Musk, they want to make a community on Mars. For us, we need to make sure the 7 billion people here on Earth, they remain great so that they can do great things, go to Mars, go to Moon. And this is the background. If we go on timeline about 25 years back, starting with the beta of the first web browser, I was working on my PhD and I kind of jumped into the web. And out of that basically came the first top digital site ranked by Computer World, one of the top search engines, social networks, and so forth. And we have been written up pretty much in most of the known technology business publications. Here are some resources I would like you to kind of make sure you are able to use. This is the online guide for the MIT executive education, which we made for the industry executives from companies like Microsoft, Tesla. This is the link which can take you to presentations from Princeton, which are focusing on not only AI, machine learning, and quantum computing, but also how to do it well, how to make sure we sustain this. This venture, which is related to Air Force Research Lab, coming from the Commercialization Academy, AML Exchange, this focuses on last 10 years R&D, and you can jump into this, go to the links when you want to later, and actually you can understand how, based on this expertise, you can save up to 90% time in execution. And this complementary venture, while we were focusing on AI, and we saw a lot of applications worldwide. We have seen that for last 20, 25 years across various areas, but mostly in defense. What we saw are there major vulnerabilities being mentioned by Pentagon, by US Navy, and so forth. So what we brought to focus was our focus here on risk and uncertainty management. That was C4I Cyber. Now, those two ventures relate to what we are going to focus on today. This is called ABMS JADC2. Now, this is like acronyms. And US military is famous for acronyms. But what are these? We'll have a look at quickly at these two concepts. What I think of them in terms of last 25 years work is they are real-time network-centric computing paradigms. These things you have seen in e-business paradigms for companies for the last 20 years. This is what the military is doing right now, how to digitize all the various kind of domains like air, cyber, space, and so forth, how to link them up, how to collect, synthesize data, and collected data make decisions and execute in real time. The RTE model which they're using here, we pioneered that about 15 years ago. You can go and read the article if you need. And here basically is the concept, the JADC2. The basic point here, which I would like to drive home, it is not the technologies per se, but the outcomes that we seek, which we need to hit. Those are most critical. In the context of e-businesses or other companies, it is the business performance. Here it is the command control. You need to make sure you are able to connect all the dots across various domains, but have the command control. Looking back at last 7 months at this evolution of ABMS JADC2, what we have been proposing is how can we extend it not only to just control, but looking at very highly uncertain environments where we have a lot of adversaries. You've been hearing about botnet attacks, ransomware attacks forever now, you know. But if I go back to one of the first keynotes in the Silicon Valley to CEOs and venture capitalists, I had titled it about 20 years ago, How to Build Digital Enterprises on the Wild, Wild Web. Coming from that, we are focusing on how do we make sure we don't get attacked, we don't go down, we can keep sustaining. Here are some research papers, some of the recent papers which go into that line, but they focus on quantum information science. And the crypto cyber, when you hear things like encryption or breaking systems or controlling systems, hacking systems, this is the kind of background of that. Coming from a background of building systems for about 20 years and then breaking systems ethically, penetration testing them, stress testing them for the last 10 years, and also training other people to do that. This is what we're trying to bring to this table here, in addition to other things. This is a focus on the AFRL ecosystem, a project recently which we proposed. Just like a Silicon Valley was a time when semiconductors were great things. Now, the time where it is, we need to make sure our things which are flying around on semiconductors and running around like cars and everything, autonomous cars, when they go out of control, we need to be able to control them so that we have the guardrails, the guidelines. And we are trying to establish those based on these projects here. Now, if you look back at all the research and development, the two key things basically which are most relevant are two terms, autonomy and control. Now, we are also pioneers in this research and development earlier, going back about 25 years when we started looking at this area, specifically in the context of how to manage uncertainty. No one was doing that work, and even now there are big gaps, and our work has been helping build practices. In fact, NASA was one of the organizations which had actually requested use of our models and methods going a long time ago on autonomy and control. And currently we are seeing the Air Force is mentioning autonomy is going to be a key thing. But the key challenge is how much autonomy you want to give. You want to have that technology, that robot do something which you want to do within certain guardrails, certain limits, but you also want to make sure it does not go over the rails. Like we have seen many accidents, technologies going out of control, which are, there are lots of examples where you can see across AI, ML, and I can bet we're going to see many more examples in quantum. And if you look at what are robots, I showed the slides for satellites. These satellites, I think my next panelist will be discussing more about satellites and QKD, which is the encryption. Those are amongst many other robotic, autonomous, semi-autonomous systems which NASA has been launching. The key challenge on the slide here is two top things here. How do we make sure we have trusted autonomy? That's a very big challenge. And that's where we've been doing foundational work going back about 20 years. The second is uncertainty. How do we handle complex, dynamic, uncertain environments? While the whole world is focusing on data now, data science, everyone is hearing data science, the next thing, we have been looking at it going back to early 90s. In fact, we rejected the notion of IT books at that time. We started focusing not on data. Data is a means. IT is a means. All technology is a means. But what are we trying to do with them? What we have been building our understanding and the world's practices and the world's understanding is, how do we handle uncertainty, complexity, change? Now, you're seeing there are other autonomous systems like this top secret autonomous plane, which can go launch satellites, service satellites, and repair satellites and do a whole lot of other things. You will be hearing a whole lot about autonomy. But the biggest challenge remains in autonomy is how do we make sure those autonomous systems, A, do not follow the guardrails because of the limitations of math. Math blows up. We have seen again and again in various domains earlier. We have seen in global financial crisis going back 10 years. And we are seeing right now, basically in the encryption models, as well as AI, and we will be seeing in quantum too. Therefore, the question here is, how do we do both things? A, make sure to have the most efficient technologies. That means they do things very fast, very quickly, but we need to make sure others don't misutilize, hijack them, and use against us. That applies to industry technologies, and this thing goes back about 20, 25 years ago when we wrote early research on business and competitive intelligence, and it ties right into this stuff here, what we are talking about, the defense side of those things. Therefore, on one hand, we want to make sure these technologies do not introduce vulnerabilities, which cause these systems to be used against us for destroying our machinery, our industries, our nations, and the world, if you may. On the other hand, we need to also look at the cyber aspects. Therefore, quantum is a very hot word. In fact, if you look back at quantum, I've been tracking this field for more than 10 years now, because my foundational work, as I look back now, after 20 years, is in defining the area what's called quantum uncertainty. And I will go to that in a minute, but many people, when they talk of quantum, they think of two things. These computers are super fast, super secure. They're not. In fact, if you log into this last this post, which I kind of showcased on one of the top labs, which is working on this, they are sharing these findings. You can click on the links and dive in, and what actually quantum is really good at. This is what I'm showing here. You can think of quantum, which goes beyond traditional data science, AI, machine learning, in terms of very fast optimization machines, exponentially fast, massive parallelism. What is that? Think of bits. Bits are the traditional binary digits, as we know, and think of qubits. When we have bits, say you got a 10-bit string, you got a password made of 10 bits. And if you see how many permutations are there, 2 raised to power 10 is 1024, okay? Now, if you use traditional classic computers, as we know, you can only check that each of the combinations 1 by 1, 1024 times, right? But if you are using quantum computers, you can check all of those simultaneously. Now, that's the basic, most interesting concept, despite there's a tons of different technologies and nomenclature, and that you can find on the site, and you can dig in, and you'll find tons of details on quantum annealing going back about 8-10 years when we started kind of researching and presenting this stuff to latest stuff called quantum volume and quantum supremacy. But let's focus on what we are doing today here. How can we understand this JADC2 and ABMS, just like in the enterprise environment? Going back, say 10, 15 years, I've been teaching grads and undergrads, how do we get real-time information using simple Excel sheets. You can pull data from various Excel sheets, pull them together, make decisions and execute. You could do that for a long time. But now what you can do is in terms of risk management, looking at risk modeling, say in financial markets. I've been advising top Wall Street hedge funds on risk modeling and risk management. Think of them as options. How can you make various decisions and how you can execute? For options to manage risk and manage rewards. That's the way, one way to look at that. The question here is in many cases, many presentations from the top labs I showed you recently, they're asking, what is the business value of quantum computing? And sometimes I wonder, geez, we are making these fascinating machines, smartest people in the world. And sometimes I say, how do we make sense of business value? Going back to our research 20, 25 years ago, where I'm looking at systems and I'm looking at the changing world, starting with the web, where you cannot predict based on past data because the future is moving so fast. And we build these models of anticipation of surprise going back to 93, adopted by companies like Goldman Sachs earlier. Therefore, we look at this phenomena called quantum uncertainty. Now, we're still building this because even in the quantum domain, just like in the AI machine learning domain, the top experts, people who are the pioneers, the creators of these technologies, many times, they themselves are biggest skeptics. They're questioning whether they got it right or they need to figure it out again, okay? Now, if we can hook this network, computer-centric modeling concept in enterprises, e-businesses, worldwide enterprises, supply chain, value chain. Similarly, we can hook it up with all these drones, swarms, and command control systems where you got big planes controlling small planes, many drones. Now you're seeing only the air domain here, but you have in the JAD system here, where you're interacting with satellite signals, which are collecting information, data from up there, interacting with the ships down on sea, submarines down in water, and so forth. And also the land forces, various control stations, army, and so forth. Therefore, we are seeing this very fast speed of light movement of data. But the challenge here is what quantum computing cannot do is telling technology, A, what it should do and what it should not. Like, for instance, here, the key challenge here basically is AI supremacy, quantum supremacy. You've seen these terms thrown around, and they are big buzzwords. What we have been trying people to kind of move beyond, we have seen this thing for 20, 25 years. Right now, it is AI quantum. Before that, it was knowledge management. Before that, it was business process reengineering. This stuff repeats again and again. All those things are means to get stuff done. What you get done is up to you. Whether you do great things or adversary things or things which kind of make the world backward, that's all up to humans. Humans are final determinants. In that context, we've been trying to help the various defense forces understand that it is your guiding frameworks. Like for China, it is unrestricted warfare. There's a big document you can pull down from one of the links and you can search on one of the sites. But for the USA, we are trying to help focus why control is a key thing. Although there's a recognition, we are trying to help understand control doctrine with the key focus on not only building large-scale systems, but also sustaining control, where you're seeing many of these encryptions being thrown apart, where authentication systems are compromised, where control is being taken off national electricity grids to dams, to satellites, to everything. Because right now the control is moving to space. Our focus on space is primarily how space can determine human sustenance, so that all the good stuff humans can do, they can go in the space and on moon and so forth. But the key point to understand is common sense that AI doesn't have. Many top scientists at AI, at MIT, for instance, have already said that. You can read their articles from many of the links here. If you go back to some of the top quants who build the strategies for Goldman Sachs, quant systems for markets, they have talked about intuition. And that's something which systems do not have. Albert Einstein, everyone knows about that name, and he talks about imagination being more important than knowledge. That is what is most critical. What we have been looking at, we've been looking very closely at all the technologies going back to before the World Wide Web, when it started in early 90s. The more we get deep into technology, the more we find there are limitations and big kind of stuff which can happen. Things can go wrong, mistakes can happen, but we need the human factor more and more, okay? What we are proposing here is there are ways to rethink systems, just like you could rethink your business systems. You can rethink your enterprise systems, your global systems, whatnot. Right now, we are on this great network, which is launched by Tian. This is what she devised. This is her creation, her idea. Just like that idea is there. I go back 20 years ago when I was giving a keynote to the Mexican parliament cabinet ministers. We had 600 people there, all the IT heads, 13 CIOs. And I shared with them story of a Mexican woman. She wanted to sell hats. And I saw her message on a data mission bulletin board. And I told them, there are people who want to do things. Make sure they can do things. They were looking back at what AI computing can do and they cannot do. These technologies can help use math computing models, collect data, synthesize, and act on it very fast. But what you do with that data, what decisions you make, those are up to you in most cases, in all domains. And recently article this came up, you can pull this link from last week or so. The chief defense officer or the UK chief of defense has said that we might be looking at World War III, and he's saying if we have 90,000 soldiers, we will have 30,000 robots in war with them. Go figure. But the question here is, what he's saying is we can have a real risk of miscalculation. And that miscalculation here, basically, he might be wondering about people, the geopolitical things and people thinking. But the key thing which I'm thinking is the technologies. If you look back at this great story coming from about 40 years ago, we had a Russian military officer. And there's a great articles if you want to read up on this person. I think we are alive now, the world is still alive, and all of us did not get eliminated. It depended on his decision one day. He looked at some signals coming on his screen, and he thought these were intercontinental ballistic missiles coming from the USA. But he overruled that. Even those signals, if we had AI, machine learning, quantum, we might be dead by now, okay? But the point here is those signals were so deceptive, so real. Nowadays, you hear about fake news, fake views, and fake voices. Those things are going to be very, very critical now. But this is the early times, 40 years ago. We didn't have web 10 years before that, okay? Therefore, it was his gut instinct. We will need more gut instinct. We will need more common sense. We need more intuition, imagination, because technology and math have very big limitations. In fact, my last three presentations at Princeton have focused on actually helping people understand, A, all models are broken, they're not real. Okay, if you focus on a model, you will go down whether you're in finance or military or whatever. Therefore, every model is a very weak representation of reality. Therefore, how do we minimize that risk in terms of uncertainty? You look at multiple models, just like you do scenario planning in going back to learning organization, so forth, okay? But the point here is more important than knowing math and computing is know the limitations. That's most critical. In fact, many people who get so much hyped about math and AI, they forget those limitations. And most critically, make sure to use your common sense, intuition, imagination. You're going to need that more and more. Now, looking back at some of these military doctrines coming out of, say, China, their doctrine, basically, they mention how to win a war without firing a bullet. And they mention that in the information age, the influence exerted by a hacker is more than that of a nuclear bomb. We go one step further. We say, given what we are observing here and focusing on the control doctrine which we are proposing, should replace this outdated legacy lethality doctrine, which has lost its lethality and its value, is that the hacker is more powerful than the nuclear bomb if she can control when and where the bomb detonates, and most importantly, make sure it does not detonate if it should not, because things can go out of control, things can go off guardrails, and we need people, smart people using smart tools who can make sure the world still exists, regardless of all these weaknesses in the very fragile math and computing which underlies many of these technologies, as well as the adversarial nature where we are seeing systems being taken over, used against them. So the key challenge, what we have seen before, is what we call the governance control problem. This is a recurring problem. Now that thing was in AI, it's going to be very much more in quantum. And we will need to make sure the Earth and human civilization, they exist, so that we can have people like Musk take us to Mars and Bezos to moon. And we can follow the role models of people like Eileen Collins. I think I was really proud of her. And I used to go to an observatory they named after her. And I used to think, what would Eileen think or do, you know? And thank you so much for this fascinating panel. And I enjoyed every bit of it.
Oh, thank you so much, Dr. Yogi. It's really insightful. It was so much wealth of information. But the one thing I noticed is, technology is an enabler, but the fundamental thing is about the data. You talked about that too, because I can tell you on the defense side, when you're talking about ABMS and everything, from our side is when you talk ABMS, let's say the one efforts, let's talk about data one. When you want to link everything, what's the fundamental things in terms of working on the standards, the policies on our end? We need a common ontology. Those are the kind of things we need to speak the same language. So what useful is data if we're not gathering and ingesting in the right format and the common ontology? So those are little fundamental things. So I also picked up that you were talking about, and also the guardrails, especially on the Department of Defense. You talked about security, multi-level security is a huge thing. I mean, still a hot topic. So I really, really appreciate it. That was really, really insightful. I could just keep going on and talking to you all day, honestly, because you had a lot of really insightful things. And I was like, oh my gosh, this is great. I just want to say thank you so much. I think we're holding, if I'm correct, we're holding off the questions till the end.
Althea, if I can make one quick observation, if I may.
Yes,
The
yeah,
point
absolutely.
about data is very critical. Sorry, can you hear me?
Yes.
I just want to make one point, one observation. You made a very fascinating comment. And that reminds me of the paper I wrote in 1995, inspired by the AI Pioneer, published in 2000, which built the foundation of this data, humans and machines. I think that paper is key. All machines, they think of data the same way. Mostly, if you program them that way, But if we share in this panel one point, we will have 100 different opinions for 10 people, So that's the difference, which has got strengths, limitations. That's what the focus of most AI systems. Go back to that thing, which contrast information data processing with sense making and how we can balance that. And the problems which military is facing, like ontologies, so forth, we've seen that earlier. We have seen that in financial markets, where at the speed of nanoseconds, they are doing this trading and so forth, high frequency trading. Now they don't have any physics of actual things to shoot. They are looking at just bits and bytes signals. But when physics comes in, we have to understand the limitations. Thank you.
Oh, I appreciate that. I probably want to get that link to that paper that you wrote there. But okay, so I appreciate that. Our next speaker is Dr. Sonali. Dr. Sonali Mahapatra, she works jointly as a space quantum technologist developer at the space engineering company Craft Prospect, as well as a researcher with an IA fellowship at the University of Strathclyde. Sonali is also one of the founding members of the New Voices in Space Working Group of the Scottish Space Leadership Council. She has a PhD in quantum gravity, it's pretty impressive, and a double master's in physics. So the floor is over to you, Dr. Sonali, and I'm looking forward to hearing the insights you share.
Thanks so much, Alethea. I'll just confirm if you can hear me properly now, and I'll go forward.
I got you loud and clear.
Amazing. So, all right. Thank you so much for inviting me on the show. And Hien, Alethea, and Malak. I'm really happy to be here. And I think I'm going to be starting perfectly from where Yogi ended his slides on. I think you gave a wonderful, fascinating presentation on what are the limitations and what are the approaches that we should take to technology, quantum technology, AI. All of them are quite related to each other. All right, so I'll give a little bit of an introduction to myself. Thank you so much, Alethea, for the intro. Currently, I am working on quantum technologies in space as a space quantum technologies developer at a startup called Craft Prospect in Glasgow, in Scotland, in the UK. At the same time, I'm also jointly working with the University of Strathclyde as a researcher, as an IAA fellow, working on similar topics as, how do we make QKD in space a reality. What I do is I work in this interface of both academia and industry so that I can very seamlessly take a lot of ideas from academia, things I work on, things other people work on, and engage a lot of researchers with industry, and then figure out together, how do we actually take some of the research ideas and translate them into actual technology, figure out the obstacles, what are the barriers, how do we make sure there's a lot of people getting engaged, how do we make sure that we raise the obstacles to the people who are in a position of making jobs available so that we can get rid of the obstacles, we can make components for space and so on. So today I'm going to be talking a little bit about currently what I'm focusing on, which is doing quantum key distribution in space. I'm currently a part of the technical team of an upcoming mission, which is known as the ROCKS mission. It is Responsive Operation Key Services, and it kind of brings together two of the things that Yogesh was talking about, quantum technologies as well as AI systems, automation. And then hopefully I'll give a little bit insight into how do we actually make sure that we are also making key decisions in there and not letting AI do all the work. Because as Yogesh pointed out, we are giving AI the training sets. So basically, we don't need to take off the training wheels just yet. We need to make sure there's human and AI talking, combination of both our brains melded together so that we can take right decisions at the right time. And talk a little bit about what is quantum technologies, why do we want to use quantum, right? So basically quantum is a study of the extremely small, which is less than 10 to the power minus 15 meters. And when we talk about quantum technologies, we are talking about manipulating single quantum particles, like single photons and single electrons, and then hoping that we can do magical things with them. So my background is basically quantum gravity, quantum quantum foundations, quantum theories. I did my PhD in quantum gravity, but at the same time, I did a lot of work in quantum computing, machine learning, artificial intelligence, and the theory of quantum foundations. Why quantum theory is what it is today, and how do we actually work on some of the things that we do not understand in quantum now. So what I have brought over to industry is that experience, and then using this experience, we'll be going forward and making some interesting things, manipulating single quantum particles such as photons, which I'm currently doing. So when we are going to quantum in space, that's a whole new ballgame. We are, so the topic of today's presentation is quantum technology is going to change humanity, right? And if we are talking about the progress of humanity through our timeline of human evolution, we will see that if you look at the growth curves, I don't have the growth curves in front of me, but this is something out of the top of my head. If you look at the growth curves, you'll see that basically it goes at an exponential, and then at some point we need a paradigm change so that we don't run into something which we call as the singularity. And I think we are at the point when in the space of one generation, right? Like basically when I was born until today, we have gone from not using that much electronics, not having electrical systems around the world, not having computers, to actually coming to the time when we are trying to take quantum into space. And so I think we are at the point where a paradigm shift is necessary so that we can actually develop what the future means for humanity. We can take important decisions, and we won't run into the singularity. So why space? Why do we want to take quantum technologies into space? First of all, space has microgravity. It does not have atmosphere. It has high vacuum levels. It has long free fall times and low temperature. And all of these combined together makes it a wonderful enabler for tests of equivalent principles, to test gravity, to test quantum gravity. It makes it a wonderful place to also let us test long distance tests of entanglement of particles. It's a wonderful place for us to take clocks and sensing equipment and then test how precise they are. We can also test very, very tiny deviations from general relativity, which is currently our understanding of how gravity works on large scales. It is also going to enable long distance global communications infrastructure, which I'll be talking about a little bit. And in the future, hopefully it'll enable us to have a quantum internet. And what I'm working on currently is how do we have better cybersecurity against quantum computers? And as part of that, I do quantum key distribution, which is one of the focus areas of quantum technology. So where is the excitement today? Quantum key distribution, as I told you. There is quantum sensing, which is basically you take two tiny atoms, you take two tiny photons and you put them together, and using the energy that goes out of the excitement of these photons, you actually make very, very, very precise measuring instruments. You can measure time, you can measure, you can make magnetometers, you can measure magnetic fields using that, you can measure gravity, which are like gravimeters. We can do quantum metrology. We can do a lot of very, very theoretical quantum physics experiments as well to understand more about the nature of the quantum space-time. All right, so let's go forward. Where were we? I was going to talk about quantum cryptography. Why do we need to make the jump into quantum cryptography? So today, as all of us know, we deal with a large amount of data, as Yogesh also pointed out. We are doing, especially in Corona times and COVID times, we're all doing a lot of virtual meetings. We're all working everything on the laptop. We're remote working. All our data is in our phones, our laptops, our banking systems. We are always receiving OTPs, the one-time passwords, which we plug into our system so that we can have secure communications with our banks, with our health institutions. So with all of this data comes a lot of responsibility to make sure that this data is protected. Today, yes, we do protect that data. We do that using public key cryptography, which is based on very, very tough maths algorithms. They are hard to crack, but they're not exactly uncrackable, right? Now, with better and better computers, and like Yogesh was talking again, even with quantum computers on the horizon, these potentially will be very easy to crack. People are projecting that in the next 3 to 12 years, quantum computers will be able to increase the complexity of the problems that they're able to crack currently. And we might be, and if you're basically a part of a crime syndicate who builds their, who gets their money every day on putting a lot of data in their computers, crunching the numbers and figuring out all your secrets and taking all your money, you would already have started collecting this data. Maybe we don't have quantum computers today who can do this cracking for us, but in the next 10 years, if somebody is collecting all our data and keeping them, by that time, they will be able to crack it and all our data is going to be insecure. So how do we make sure that we can protect our data and make it future-proof? That is the big question. Can we actually take the basic theory that quantum computers use, which is quantum theory, and can we turn it on its head to make sure that, okay, quantum computers can crack the data? Can we also use quantum to protect our data in this case? And this is where quantum cryptography comes in. Quantum cryptography, in turn, uses quantum objects like single photons to encrypt information. And the good thing about the QKD that currently a lot of people in the world are trying to do is that if someone else tries to capture those photons mid-channel and they try to figure out what kind of information is being sent from A to B, we will always be able to tell if somebody is trying to eavesdrop. So we might not be able to protect all of the, we might not be able to stop them from eavesdropping, but we will always be able to tell in the first few minutes of trying to set a secure key that somebody has tried to eavesdrop on this, and we will just abort that particular communication channel. So it is going to be future-proof in that way. Now, let me go to the next slide. So what exactly is quantum key distribution, right? So let's imagine two people. One is Alice and one is Bob, which is the usual terminology when you talk about quantum key distribution. What Alice is trying to do is set a secure key between herself and Bob so that they can use this key in the future to communicate with each other. So basically my yellow flickering dots are the quantum particles, photons, which are being sent by Alice to Bob. And Alice, what she does is uses the quantum particles of these photons, which are known as polarization. They can be something else. So in our case, we use the polarization of photons. Either photons can be polarized vertically and horizontally. They can be polarized in a diagonal, anti-diagonal manner. And so we can say that if the photon is polarized vertically, we say the information is 0. If it's polarized, horizontally, we send 1. So that's the way you're using some kind of a library to send information between Alice and Bob, right? So now what happens is after Alice and Bob, basically after Bob receives this photons, he'll be able to perform some measurements. He'll be able to figure out what information Alice has tried to send him, and they will be able to set a secure key, after which they will be able to do secure communication within each other. But the problem is today there are a lot of companies who are doing already QKD commercially. They're selling commercial QKD setups. But terrestrially, currently we're using fiber optic cables to send these photons from Alice to Bob. Now fiber optic cables come with their own problems because photons are tiny particles, right? Fiber optic cables come with a lot of losses. Now, if you're trying to send these photons more than 500 to 600 kilometers, even after using repeaters, you can't do that after 500, 600 kilometers. The photons are going to denature and break down, and there will be no secure key set. So what do we do in this case? Because at the end of the day, we want to make sure that the whole world is connected using this quantum key distribution. We want to take security as a blanket to the whole world rather than only bubbles of 500, 600 kilometers on Earth, right? So that is where space comes in as an enabler. So what I'm trying to do is give you a very simple story of how do we actually use space as an enabler to augment our secure systems on Earth right now. So it's not a problem if somebody wants, somebody is, let's say, Hien and I don't know where you are based currently, Hien. Where are you based?
Germany.
Right. So Germany, I'm sure, we are not in the same country. We are not within the 500 kilometers radius. So if I want to communicate with Hien secretly and securely, I don't have to panic. What we have to do is basically I have to set up a ground station in United Kingdom, and Hien has to set up a ground station in Germany. Now, what that looks like is something like this. And what we will be doing is we will come to an agreement to send up a satellite together, right? Now, this satellite, what it's going to be doing is it's going to be going over my ground station at some point. It's also going to be going over Hien's ground station at some point. Obviously, we'll have to choose the orbits of the satellite quite carefully. The good news is once the satellite is up, when it passes over myself, I'll ask the satellite to open a quantum channel. Now, this is very much Star Trek-like, right? So what the satellite is going to be doing is sending down single photons to myself. And when the satellite passes over Hien's ground station, it's going to be sending down single photons to Hien's ground station. Now, why can we actually do this from space? The good news is because we are going to be sending up this satellite in a LEO orbit, which is 500 to 600 kilometers, right? So essentially, this is acting as a relay. We're cutting down the 2,500 kilometers between both of us into 500, 600 kilometers because the satellite only needs to send photons 500 kilometers down into the Earth. We have other good news, which is that in Earth, the atmosphere is basically around 10 kilometers, let's say, at some of the, the narrowest levels. So the photons travel most of the time in empty space, which is how we are breaking down the losses. We are making them very negligible. And so there's not that much atmosphere for the photons to collide with and denature. There's also no fiber optic cables that we'll be using, and they would not be inputting losses into our system as well. And so, yay, we have some very nice empty space through which photons can travel and come to our ground stations. And we do, this is not as easy as it looks, right? This is a simpler picture. This is the basic picture. But at the end of the day, we'll have to figure out what kind of satellite are we going to be using. We'll have to come to a treaty. We'll have to build the quantum source, which fits inside the satellite. We have to think about whether we should be using single photons, whether we should be using entangled photons, whether we should be using quantum random number generators to improve the security of our system. What kind of quantum sensors do we need to use? What kind of detectors should we use on the ground station? What kind of telescope we should use? How do we measure quantum states? How do we ensure that the timing, like the satellite sends the first photon and the ground station understands that, yes, this is the first photon that was sent at this particular time. So it's a lot more complicated than it looks. And that is why we have some of the best minds in the world working, computer scientists, physicists, mathematicians, industry people, project managers, everybody working together to make all of this a reality. Now this is all well and good. But if we want to build towards a global quantum network, we want to have like some kind of a quantum internet would require a constellation of satellites around the Earth. We need smaller satellites. We can't do that with conventional satellites today, which are huge, bulky. They need customized systems. They need to bring together a team of thousands of people. They need to have a lot of funding. Now, smaller satellites, on the other hand, have more risk appetites. They are less costly. They're easier and faster to deploy. And so this is what has brought us to CubeSats. Now, CubeSats are actually very cute, tiny satellites, which are, if I want to give you like some sort of a scale, then imagine your cereal carton box. You have cereal in the morning from cereal cartons. That is basically the size of a CubeSat. It's that big, right? And so even though it seems like these are smaller satellites, we're going to be spending less money on them and we can send them much faster, right? The problem is that we have to take a whole optics table in a university and then miniaturize it into this tiny payload, which can then go into a satellite and can do some very, very cutting edge quantum key distribution. So I have some pictures of a 12U. CubeSats basically have like a unit system. So 1U is a 10 centimeters by 10 centimeters by 10 centimeters, as you can see. And to scale, I have a loaf of bread right there. So they're very tiny. And it's very useful to have them. You can just have them very easily. Anybody can buy them nowadays. And this also leads to like democratization of space. You know, not only big organizations and government can have access to space, but a lot of startups, a lot of universities, a lot of school children can also have access to space. A lot of people have built CubeSats. They have put sensors in them. They have put images in them, cameras in them. And some of our wonderful data, very, very important data has come from these CubeSats built by students, right? And these CubeSats were actually started as an enabler to help university students understand how do you actually send up a satellite. But then we figured out that, you know, CubeSats are way too valuable to make it only available to students. So now a lot of startups and government and organizations are using CubeSats. Now at Craft Prospect, what we are currently doing is we are building a payload of a quantum key distribution system to go in a 6U CubeSat. So you can see on my slide, the blue box over here is basically the CubeSat bus in which we will be putting this payload. This is basically our optics box, which is going inside that CubeSat. And inside the optics box, we have a laser system, we have collimators, we have various mirrors, we have dichroics, we have lenses, we have 3 or 4 lasers, we have all the electronics that are going to go inside of it. And it's amazing to me how small electronics have become today. Like we can build anything starting from an Arduino, right? A robot toy or something that goes into space to provide us security. Right, and we are not the first people to do this. ROX is going to be one of the first CubeSat missions in the world to be launched in 2022, which is going to try and demonstrate satellite to Earth quantum key distribution using a WCP, which is a weak coherent photon laser source rather than a single photon source. But the first mission which demonstrated this was the Chinese mission MICEUS. But MICEUS demonstrated this on a conventional satellite. And it made video conferencing possible between Austria and China with a secret key. RAL Space, which is a UK-Singapore consortium, also is trying to do an entangled photon source mission, which is probably going to be around 2022 as well. There's the KeySat Canadian mission, which is going to be having an entangled source on the ground. So it has flipped the whole picture that I showed you. The source is going to be on the ground and the quantum channel is going to be opened from the ground to the satellite. And we are working with quite a few consortiums around the world to do this. But before I go further, what I want to point out is on ROCS, why it is called ROCS, Responsive Operation Key Services. We are also including automation here. So we want to make our satellite responsive by itself so that we don't actually lose a lot of resources. What we are doing is we are putting a camera imager on the satellite, and we have our first product, which is known as the FLY, the forwards looking imager. If you go on our website, you'll see a lot of details about it. It's already out there. What the FLY does, it looks ahead when the satellite is, it's going in its orbit. And before it needs to open a quantum channel with a ground station, the FLY is going to look ahead and see if there's something that is going to block this happening. Right? So the FLY takes a picture, it sees that if there's a lot of cloud over that particular ground station, if there is cloud, it says, it sends a signal to the brain of the whole system, the computer, that, hey computer, there's cloud over this particular ground station, so I won't be able to do a proper key distribution here. So let's point ourselves towards another ground station, which is free, so that we are not losing a particular pass. We are not losing one orbital pass. And so that we are making very efficient use of our orbits and time, right? Right. So now, this is basically what ROCS is all about. And currently we are also starting to think about how to we offer QKD commercially, a QKD consultancy to a lot of different startups, to a lot of different ecosystems, to also universities. We work very, very closely with universities and undergrads, master's students, PhD students, as well as professors, all like bringing the whole ecosystem together, really. So because there are a lot of challenges in this field. Now, theoretically, the work has matured, but technologically, we are, like all of us, are actually doing this all for the first time. That makes it really exciting, but it also makes it really difficult, right? A lot of innovation is required. You need to understand how to take like a whole big optics table, how to make it extremely small and still make it work even better than something that would work at an optics table on Earth. We have to manipulate single photons. We have to understand how do we do long distance entanglement, teleportation. We have to understand the risks. We have to figure out how to miniaturize quite a lot of electronics and devices. We have to figure out what kind of radiation levels are there in space. How do we make our systems radiation hardy? We also have to think about that, if you do something like QKD, you have lots of tiny little optics in that box. So because we will be doing a launch in a much bigger launcher, which are not built for CubeSats usually, how do you make sure that these tiny instruments do not break during launch? How do you actually fit everything inside a CubeSat? You have lots of lasers. How do you do laser safety? And apart from these, how do you standardize all the components so that different missions around the world can actually talk to each other in the future and can form a constellation together? Do we have any regulations currently? No, we do not have any regulations. So we're also working on big consortiums to figure out what kind of regulations should we already have so that we do not have some kind of collisions between different satellites in the future. We do not have piracy, space piracy, which instead, unless you actually plan for these things, will happen. So yeah, there's lots of interesting work going on in this arena, but there's lots of challenges and there's lots of things to be getting involved in, lots of opportunities. My team at Craft Prospect is quite balanced. I'm very happy to say we have almost 50-50 gender balance, which is great, which usually is not heard of. But what I'd like to also point out is because I do a lot of EDI related work, I'm usually a big champion of innovation, which comes with diversity. And unless you're improving and including diversity in your team, you're going to be leaving out quite a lot of very important or good ideas that a lot of other people will have, right? Evolution is all about variety. So be smart, bring all the variety in, right? And you'll see great things happen. So thank you, everyone. If you have lots of questions for me, I'll be happy to take them and happy to discuss other things with this as well. But thank you so much, Ian, for inviting, and thanks, Alethea, for the introduction.
Thank you, Dr. Sonali. That was one of the most exciting presentations on quantum technologies. I mean, your passion, your excitement really exudes out. You raise a lot of similar points in a different lens from what Dr. Yogi was talking. We talked about, it's all about the data. You talked about cryptography. Its security is still very, very key. You talked about standardization. We talked, Yogi and I were talking about standards just now and the regulations of it. The one key thing I also thought that you really, really hit on also was the paradigm shift. This is going to take a culture change. It's an ecosystem. And I'm 100% with you. When I was doing my MIT fellowship, the one thing I learned is everybody comes from a different lens. We all come from a different lens, different perspective. So everybody needs to be part of this ecosystem. So I'm just applaud you for all your efforts. Thank you for sharing this. In the interest of time, I'm going to move on to the next speaker and then hold off till the questions later. Thank you so much, Dr. Sonali.
Thank you so much.
Our next speaker is Professor Clarice Ayilo. She's a quantum engineer interested in how quantum physics informs biology at the nanoscale. She's an expert on nano sensors harnessing room temperature quantum effects in noisy environments. Ayilo received her PhD from MIT in electrical engineering and held postdoctoral appointments in bioengineering at Stanford and in chemistry at Berkeley. She joined UCLA in 2019, where she leads the Quantum Biology Tech Lab. Very, very fascinating background, and looking forward to your presentation. Over to you, Professor Clarice.
Thank you all very much. Good morning, everyone. My presentation will start somewhat funky, and I'm going to get to space a little bit towards the end, and you're going to see what a journey this is going to be. So I like to call myself a quantum engineer. This means that I'm trained as a physicist and that I develop apparatuses to study and control things that are so small and so well protected from their environment that are better described by the laws of quantum mechanics, as opposed to the laws of classical mechanics that we learn in high school and that rule everything big around us. So it turns out that there's a lot of mathematical findings that posit that if you use a quantum object as a sensor, if you use a quantum object to determine, to measure things such as magnetic fields, electric fields, temperature, your measurement is improved. In other words, the sensor quantumness enhances your measurement. And I think it's important to say that I believe humankind is obsessed with measuring things better, because this means that we understand things better. So one can talk about measuring, yeah, there's a delay, measuring better frequencies. This is an atomic clock that exists in NIST in the United States. NIST is the American equivalent of the PTB in Germany. It's the institute that defines standards. And with this atomic clock, one can define what a second is based on atomic transitions. And as you can see, something that already relates to space is the fact that this atomic clock, you see this very long column there. This very long column, actually, you have atoms that are dropped that go from the top of the column to the bottom of the column, and the height of this column sort of limits how well you can do your measurement. And some people are starting to take atomic clocks in space because you're no longer limited by a following sort of distance, right, because of microgravity. So this is to some extent a technology that is being translated into space. So we might want to measure better frequencies. One might also want to measure better magnetic fields. So this is the magnetic resonance image of a baby inside the mother's belly. And in magnetic resonance imaging, the better you can measure magnetic fields, the more resolved your baby's picture will show up. And we can also think about measuring, for instance, better accelerations so that your gaming experience is enhanced. Those tiny little accelerometers are not ubiquitous in iPhones, Android phones, and also in mobile video games. But the question that I ask is, and the question that guides my work and my presentation here is, what happens if the quantity that you want to measure is very, very small? Or worse, what happens if the object that is causing this quantity to be measured is very, very small? I'm going to briefly argue that in this case, you need a tiny little sensor that is able to measure tiny little quantities. And if this sensor is tiny, let's make it very tiny. Let's make it quantum. Again, there is a lot of reasons why that might be so theoretically, and it has been shown also experimentally that the sensor quantumness enhances the measurement. So in my past, I have worked with two different, what I'm calling technological quantum sensors. One was a magnetic field sensor, and the other one was an imaging sensor. Those two only worked because they somehow relied on quantum mechanical properties. But importantly, they worked at room temperature, okay? When we think about photons are a little bit different as quantum objects, but when you think about other types of quantum objects, quantum computing, we usually think of them in very protected environments, in a vacuum, cooled down to millikelvin temperatures. So the technological quantum sensors that I worked with, they worked at room temperature and in what I call noisy environments. And by noisy environments, I mean they were very good sensors that worked in the proximity of biological samples. So at this point, I'm actually going to be, I have a couple more slides, but I'm going to stop. So I'm going to stop my slides to tell you where I'm going with this quantum sensing talk, why I believe quantum sensing goes beyond technological features, and how I think space might be an important frontier in what I want to explore. Right now, there is enough, but not complete evidence that organisms might, like living things like cells and organisms, both small and big, might for a very short time be using quantum properties that are very similar to the properties that technological quantum sensors use in order to interact with their environment. Okay. If that's true, if the evidence holds up, this means that organisms might, for a very short time at room temperature, be behaving as living quantum systems, living quantum sensors, if you want. So the whole idea of my program of research at UCLA is to take quantum-inspired techniques and machines and start applying them directly onto those putative quantum objects inside organisms in order to sort of understand whether this is, and either confirm or refute whether this phenomena is true, and maybe start learning two things. Either like if nature really is harnessing quantum mechanical degrees of freedom for something, can we learn with nature to improve technologies? And in the sense that, for example, quantum technologies suffer from noise. Everything that starts quantum dies classical, and that's mostly because of interactions with the environment of where the quantum system is embedded. So the idea is, if nature is actually using technological elements of quantum mechanics, can we learn, especially how technology deals with noise, in order to apply those laws onto technologies like quantum computing technologies, technological quantum sensing technologies. The second important part of our research has to do with, if nature is using quantum mechanical degrees of freedom, can we commandeer physiology by tapping onto those technological degrees of freedom, by trying to control those degrees of freedom in the same way that one would try to control quantum bits, right? May they be photons or other sorts of quantum computing units. But in this case, they just happen to live in a wet, hot environment of a living system. I want to give one example, and I have some props for that, in how exploring quantum mechanical degrees of freedom in biological things in space might be important, okay? And one of the technological quantum sensors that I worked with was a spin in the material diamond that was briefly on my slide. And with that sensor, we could sense magnetic fields like many times smaller than the Earth's. And the Earth's magnetic field is about 50 microtesla, which is weaker than the magnetic field that you sense when you put your cell phone close to your ear, right? So this can be done with technological quantum sensors. However, it has been known for decades now that even if only as a partial cue, that birds and butterflies and turtles, they do use the magnetic field of the Earth to migrate when they migrate north to south and vice versa. Which is puzzling, right? Because it's not really known how they do this, but people who study animals in a large scale, they know that they definitely do. So in the beginning of the, actually end of the 80s or so, biophysicists started trying to understand how that could be so, right? And it turns out that in basic chemistry, and I'm a quantum person, but I do need to tell you a little bit about chemistry and other things, which is all of the fun that comes with working in this area, because there are elements from several subjects. So biophysicists, they remarked that in basic chemistry, there are processes whereby chemical reactions are influenced by magnetic fields by means of spins. Okay, so physicists usually represent spins with an arrow, and spin is a merely quantum property that some particles like electrons have, and that is a measure of how well they interact with magnetic fields. And spin up and spin down only mean two different energy levels of this merely quantum property called spin. And in basic chemistry, it's known that there are chemical reactions that depend on magnetic fields, in the sense that a magnetic field can alter the energy levels of a certain spin. And some chemical reactions, they are spin dependent, in the sense that the reaction continues through one branch if the spin is measured to be up, and the reaction continues through another branch if the spin is like, if the spin is down, and up and down is altered by external magnetic fields. Importantly, the end products of those two branches that depend on magnetic fields, that magnetic fields can alter in the very beginning, the final products of this long chemical reaction, they are macroscopically different. So it's in this sense that a spin finicky quantum property and an interaction with a magnetic field happening at the top of a chemical reaction can give rise to different macroscopic final products. This is known in chemistry. Biophysicists, and then it was just a theory, they posited, well, maybe if such magnetic field dependent reactions involving spin were at play in, say, birds, birds could sense the magnetic field to the extent that they could sense the different physiological concentrations of products coming from such type of spin-dependent chemical reactions. Okay, so the birds wouldn't care about the magnetic field, but they would care about physiological concentrations of products. And this is where this field all started, when people wanted to try to understand like bird and big organism navigation. Right now, there is evidence both with birds and at the nanoscale, say with vials of proteins, that spin is a thing that is very likely being harnessed by nature when organisms want to feel and react to magnetic fields with important consequences. So one thing that, so what I do is the evidence that exists today, exists at two disconnected length scales. There's evidence with like vials of proteins, and there's evidence with like whole birds, plates of cells, and we want to bridge those length scales by doing experiments with, say, single proteins inside cells, and do what I would qualify as a quantum sensing experiment, but just happening not inside a technological quantum sensor, but inside a living quantum sensor. So what the hell? What does it have to do with space at all, right? Interestingly, it has been shown on Earth that tiny changes in magnetic field environment do crazy things to development of embryos, to metabolic processes, to the way plants develop, right? So one of the things that I'm interested to do is try to do ground research, emulating magnetic field conditions in space, to try to see if we find a way of understanding and predicting what might happen to living organisms when they are exposed to different magnetic field conditions that one may find in space. For instance, I'm arguing that colonizing Mars needs to pass through a study of what sort of magnetic fields might be encountered in Mars. If you go for like a 20-year journey to explore living planets, and you need to be self-sustained, you need to grow lettuce and tomatoes in space, you need to reproduce in space. What's the magnetic environments that might actually affect your spin, right? So what are the considerations that we need to take right now in order to consider those biological aspects whose evidence is consistent with depending on a quantum property. And now I would like to go back to 2 of my slides. Sensing phenomena that might be explored by organisms in general, and that can feed back and forth between technologies, right? And feed back and forth between ways to treat disease. And my final point is that the final frontier of space, in my opinion, passes through the understanding at a quantum level what happens to organisms when they are exposed to the weird, especially magnetic conditions of outer space and of other planets in general. The lab that I lead at UCLA is called Quantum Biology Tech, or Qubit Lab. And my email at UCLA is just cla@ucla. So feel free to contact me if you're curious about quantum sensing and in various contexts. And thank you for having me here.
Oh, no, thank you so much. That was such a fascinating presentation. And you know what? I love that play on words on your lab, Qubit. I feel like if I'm in California, I got to come and visit you at some point.
Yes, by all means.
I know. And you raised up so many interesting things. So I'm an aerospace engineer. I come from a flight test background. So even though, we're, different in that aspect, when you talk about noisy environments and everything, I mean, in terms of that, variation is inherent in our system. So we also consider that. And you talk about the measurements and enhancing it. I mean, these are stuff to enhance your models. When we build a flight envelope too, we build upon it. So love it, love it, love it. You also brought out a lot of points, and it's not only applicable to space, but everything you're doing and researching on is very, very key to multiple domains. So I'm so excited about what you come up with. I'm looking forward. I'm going to Google about your biotech lab. Do you have a website? Because I'm so interested in what you guys are doing. So yeah, no, I guess I'll get it from you. I'm sure they will share it with us, but just definitely a fascinating work. And overall, I mean, there's all these 3 presentations. I mean, we learned about quantum technologies, but the profound effects it has it's optional. It's just impactful. So anyway, I'm super excited about everything. I could just keep going on. This is so fascinating. I'm so happy that they invited me. So I guess now it's open for Q&A.
The first question it is what are the progress made in the field of teleportation through the use of quantum technology? Is it possible through quantum technology?
Yeah, quantum technology definitely can support teleportation experiments. In fact, the MyCS satellite did successfully do a teleportation experiment. So basically, they used two entangled photons, one on the satellite, one on Earth, and they did show data transfer, information transfer between the 2 quantum particles. So I'm sure a lot of people, you can find a lot of articles on teleportation out there, and everyone maybe understands that teleportation is not when you're sending matter instantaneously from one point of space-time to another point of space. But what happens is the matter stays where it is, but you're actually taking the information inside of the matter and transferring it. Currently, we have managed to do that in single photons. We have managed to do that, I think, also in atoms in some labs around the world. And recently, there has been publications regarding quantum teleportation between qubits. I think there's still some controversy going on around that, and I'm sure that will be cleared up in some time. But yes, there is hope, and quantum teleportation is absolutely possible.
Perfect. Thank you so much. Is there any other panelists would like to add to the answer of Dr. Sonali?
Yeah.
Okay, I think if the participants interested in can we kind of energize and go to moon, I think that is a long ways off. I think the issue about matter and energy. But I think that's where Professor Clarice, your presentation was fascinating. So was Sonali yours. Now I understand a whole lot more. Both your areas have interested me a whole lot, but I think it's fascinating presentation, great. But I think I can see connections here between the biochemical, electromagnetic. There's a whole lot of stuff I've been looking at what biophysicists have been doing, but I think it has not hit the mainstream yet. And we are waiting for that day when we have this understanding for biological, chemical, electromagnetic systems. And I think that will have very significant implications for the stuff which you are doing, Alethea, in your context, in the aerospace domains and whatnot. I think you have beautiful synthesis of all these things, and I'll look forward to that. Thank you so much.
Thank you, Dr. Yogi. And also thank you, Dr. Alethea, because actually you are moderating the show today. And you are coming from quantum technology background also, and maybe we will have some questions for you to answer. And the industry now is not ready for switch to quantum technologies and or quantum computer. We do not need to be watching the person, and actually he's a doctor in Aero. Actually, he's a doctor in quantum, and he's my tutor, and he is following. So he's saying that so we are not ready for the quantum computing right now. So when AI, artificial intelligence, will reach its limit. So this question, I think, is for Dr. Yogi, and Dr. Alethea can help us if she likes to add.
I think this is a fascinating question because we've been hearing about singularity for a long time. Ray Kurzweil is the big name, I think very famous person. About 20 years ago, I had my undergrads go hack his Ramona, his avatar bot. And we used to trick that bot and make it fail every time. And over 20 years, I've watched AI progress a whole lot. And even right now, I find it fascinating to see that top MIT computer scientists at MIT, CSAIL, and so forth specifically mention AI has no common sense. I think that's fascinating. When in sixth grade, I had my English teacher, Mr. Williamson, who said common sense is very uncommon. I didn't know what that means, but now I a whole lot appreciate that. Therefore, common sense, AI is very limited. In fact, there are people at MIT, both in psychology, computer science, and AI. They have criticized that most of this AI is computational statistics. And there are people in neuroscience there who had some of the biggest programs. They are saying the future of AI is yet to come. And we can see the connections between the work in AI, things like neuromorphic, we're hearing a whole lot there, and so forth from companies like IBM and Intel. But I think we're going to see this merge at some point. And this will be a fascinating intersection where these things are going to go. And right now, I think we are just starting. And there's a whole lot further to go. When you hear about advanced general intelligence, and I think AGI, if you look at actually the physical, electronic, and even chemical properties of human mind, brain, which we are still trying to figure out, you will see the human mind is still the most complex, most efficient, and most effective processor compared to anything out there. Even the human eye itself, by itself, I think most supercomputers can't match that power. You can see these things mathematically, computationally. Therefore, I think these things we are still exploring, and we're going to see a whole lot in the future. But I think all other three very, very smart panelists who know a whole lot more about these things can add further to what I just shared.
Yes, thank you, Dr. Yogi. For sure, I will ask also Dr. Alethea and Professor Clarice about that. Where are we with the AI and quantum computing? And quantum computing will unleash the what we are waiting for, or people are scared of, you know, with the artificial intelligence. What is the future, and how it will be? Let's say how it will be functioning and commercialized and given the result that we are waiting for.
So the one thing, yeah, the one thing I would say, I think Dr. Sonali kind of hit on it. You know, when I came in, I said technology is enabler. A lot of the things we see now going on, okay, virtual reality, I mean, it happened decades ago, but now you're seeing the unblast of it. Why? Computing, data, access to it, of how we do it. But the fundamental thing, I think, at least from my standpoint on Department of Defense, is the cultural change. It's the culture change, what we call the frozen middle, people who just don't want to change the paradigm of how we do things. Look at your iPhone right now, you know, back in, you know, when I have an update, I update, it updates everyone. But in terms of Department of Defense, of how we do things, is a culture change for us, because let's say when we train as we fight, we have siloed, disparate systems. So when we update something, it has to be updated one by one. So a lot of things I see fundamentally, when you say that, the fear is a culture change, a paradigm shift. So that to me has been my one of the main pain points in terms of going. I think technology, like I said, is an enabler for us. There's a lot of things that can be understood and everything of how we harness it. But it is, and the fundamental to it is the data. How do we capture it? You know, data in, data out. So it's like garbage in, garbage out, right? So we want to make sure that we capture the correct data. It's objective. So, I mean, that to me is how I see it. So.
Thank you, Dr. Alethea. So I would ask Professor Clarice also.
So I concur with Dr. Alethea is saying. There's some things I would like to add. I think that in the quantum sciences, AI is starting to or machine learning is starting to play a role in terms of materials development, in the sense that AI algorithms, because they're just following rules, they can predict materials that satisfy, that have good quantum properties and so forth, right? So I think this is going to be booming in the near future. And I think that Dr. Alethea, I think she alluded to this, but I don't think, forgive me if that's not what you meant to say, but what I hear is the following, and which is something that I agree with. AI and machine learning, they're good to handle data and huge amounts of data, but I do not believe data is exactly equal to knowledge. Right, data per se, is nice to have, but it's not the full story. So I think that, again, before AI learns to make sense of the data at a higher level, which right now only the most complex AI is only human beings, as far as we know. That's I think is the limitation.
I think there are two fascinating points I heard, if I can relate to both of them. Let me start with Professor Clarice, your point, data, fascinating observation. In fact, data, if we go back 20, 30 years, data has become the biggest adversarial enemy out there. We got so much misinformation, fake news, fake thing. I think that's very critical now. And if I relate it to the security and risk management, zero trust architectures, we can't trust anything out there. Most of all, I can't trust my smartphone. My wife and daughter, they use smartphones with apps. I never put any apps, even Zoom. I don't want to have anything. I don't want to put any information there. I don't even want to trust any information on my machine. The kind of cryptographic models I'm thinking about, based on my understanding and the papers I'm writing, is only cryptographic models or anything which is safe is something which has got a human subjective meaning, which only you can unlock. Anything else you put out there, it is already compromised. Assume that. Therefore, if you put any information, and I have some papers on that, going back to Shannon's information theory, and that's a paper I wrote about the Shannon's work, going back to the machines, how they make sense, and the fundamental gaps between how humans make meaning. A lot of work goes back to AI/ML. It goes to crypto. It also links to quantum. And we're going to see a whole lot of stuff there at some point. But the issue is, I think the cultural issues are very big. And again, I have heard at the very biggest companies. About 20 years ago, Intel came to me for next generation e-business architectures, and they wanted to focus on culture as a very specific thing. A lot of my work in the background goes into the sociology, social psychology, and so forth. In the last 10 years, I've gone back on the engineering focus, quant, mathematical, heavy AI/ML, quant, cyber crypto, quantum. So I kind of see the links between the two. And going back to the people who inspired my work, Herbert Simon is one of the Nobel Prize winners in IT, and John Holland, who inspired my paper while he was at Santa Fe Institute, 1995 is when I communicated with him. They understood both the machines and the psychology. And that's where I can see the links between the work, between what Dr. Sonali and Dr. Alethea are doing and Professor Clarice. And I think the trust issue is very core. The smartest people out there in cyber who actually own the biggest hacking and security organizations, they think smartphones are dumb phones. In fact, when I teach my undergrads, I think smartphones are what make you dumb. You can't trust anything on that. And therefore, I think, especially when you look at national security, When you hear news of the German chancellor's phone already being compromised, think what the implications could be. Those things are real things. When you know the networks on the Air Force One, they have been compromised. You need to understand that. For me, all the theory books, courses are good, but the real world is telling us where it is going, and we are seeing real data coming in from there. And I think that relates to many of the participants here. Therefore, I think when I started teaching e-business going 20 years ago, I told my students, look at everything in the book, but if you see in the world something is going different, cross it out and change it. Because all your books, courses, everything, by the time you finish them, they're already obsolete. And that's very critical. Knowledge, data. Data has got nothing to do with knowledge. Earlier, I used to think when I wrote the paper, data and sense making. Right now, I think our reliance on data is most dangerous given the current era in which we are living at all levels. I would not trust any data at face value. And I think many people in machine learning, they are coming to that level where they said, let's pick big data. Now they want to go to small data, but most critically, they're looking at data integrity, which is the core issue, whether you can trust any data. Like, how do I know if I'm talking to you on the internet? You're a dog acting as a person, or an extra ET, I don't know, or my enemy, I don't know. The point here is, how do I trust? And that is a very human thing. Just like we're able to interact today as a community, able to interact. I think this is so valuable, so precious. I don't think technologies can ever get there. You can have avatars and whatever, you know, the holograms and AR, VR. Those are great technologies, by the way. But I think the humans in ourselves, our essence, our energy, I think that is something which technologies can't match. The deeper I study technology, the more I find humans interesting more and more. Thank you.
No, yeah, I fully agree on that, because, you know, like I said, you know, garbage in, garbage out, right? For data, it's how you exploit it. You can skew it. I mean, let's say statistics itself is how you skew or present the data. So completely agree. I fully believe a human, that's why it's the pain point for the culture. The human is the key point. The human in the loop. When you say unmanned aircrafts, there is more humans in that loop to actually operate that. That's why I said fundamentally, that's so important that you cannot replace even the ethical AI, you know, in terms of you still need the human. And at the end of the day, that we are the key to everything. So I fully concur. I think we're all agreeing on it.
Yeah. I also wanted to like quickly jump in and just touch upon that social, the cultural, the psychological, the sociological factors. It goes into so many human domains that we don't even think about it, because upskilling is a big area of how do we actually make that paradigm shift. Now we are focusing on upskilling. So some sort of upskilling just happens naturally and culturally as time passes, right? So when I was introduced to computers, I was told very, very much that do not ever, make sure that you don't take out the computer, like break it apart, and because we didn't have the money or the expertise to put it back together, we won't be able to buy another part if necessary. But now students are learning exactly how to open up the computer, how to build robotics from Arduinos. Things are more accessible, and accessibility is a big issue in making something, into making something evolve much faster than it would otherwise. And the second is, what do we actually put in our education curriculum? Which age children are learning this, which age children are learning that. So at some point today, we don't understand quite a lot of things very much, but the next generation humans will, and they will be paralleling, machine learning evolution and, human intelligence evolution at the same, well, not at the same rates, but hopefully at rates that we can work with. Yeah, I just wanted to put my 2 cents in there.
So here, is the communication going to be cost effective? And I think maybe Dr. Sonali, it's for you, because you spoke about quantum communications and satellite deployment and so on.
I mean, we are definitely trying for communication to be cost effective. At the moment, these kind of experiments are. The status is that everything is new. We are working at the cutting edge, the bleeding edge of technology, and that is why we are shifting to CubeSats to make sure that we are going from order of magnitudes of 20 million or a billion to 1 million to 2 million per CubeSats, and per whole system, 3 or 4 payloads put together. And again, I know that university students send up CubeSats on a regular basis, and those have an order of magnitude less cost as well. So the idea is to make communication cost effective. The idea is to make it more accessible at the end of the day, so that we can actually build up our quantum networks around the world. Otherwise, we won't be able to build up this network because not many people can afford them.
Sure, thank you.
she has any thoughts, please go ahead.
Professor Claris is about quantum physics and consciousness. And this question is lots and lots of specialists and scientists, they had that question and they tried to figure out, because actually from physics and how that would go into our biology, and within the temperature of our brains and neurons and everything, how does it work? And can you answer that, Professor Claris?
Yes. So I don't know how it works, and I think they're still going to need a long time until we make all the connections needed to, if at all, relate consciousness to like the hardware, right? At this moment, I do not know whether it is related to necessarily quantum phenomena, even though there are some proposals on that, right? So I'm at this moment agnostic, but this said, I think that there's a lot of small steps that we can start taking experimentally, that will at some point allow us to either refute or prove something like this. But yeah, I think all research that goes in this direction is worth undertaking. It's nice, but I think that we need smaller steps. So I'm going to cite one thing that I'm less skeptical about, and I think that is very cool. It doesn't really relate to a consciousness per se in the big scheme of things, but it does relate to how general anesthesia works. And there is evidence, sort of not complete, that the way general anesthesia works might involve spins at some level. I won't say anything more about it, but yes, I think it's worth exploring, and we need many steps to be able to make like big conclusions, and like we need extraordinary evidence to make extraordinary claims. But maybe we'll get there, and maybe we won't, but maybe we'll understand things getting there.
I think I can add something here, if I may. Going back when I was doing my PhD long ago, everyone in IT was focusing on IT, and I was too. How can we automate everything, make humans disappear? We will put everything on automatic. Everyone wanted to do that, And one question which I got fascinated in, which John Holland got me inspired, interested, is how does information become meaning? That's what he asked. And I said, everyone says IT is there and stuff happens. What are the gaps? Data is not stuff what gets things done. If machines and robots were there, yes. When humans come in, it's the different interpretations of data, different between different contexts, different time. Even at the same time, any human can look at any data and hold multiple views of the data. We can look at multiple futures, multiple times. We are quantum beings if we kind of apply our minds, but we kind of focus too much on technology and forget the power we have. And at that time, basically in that paper, what I came to realize, based on a lot of work in human learning and sense making, it is not only cognition, it is the emotions called affect. And finally, it is the action, the act of actually doing or thinking that you're doing. There's a lot of studies on actually doing stuff in your head and actually doing. And they show there are parallels in those studies have been there for a long time. Now, I also know of a person called Antonio Damasio. If you've heard of a book called Descartes' Error, one of the most fascinating books I studied during my PhD, and that was about how the human brain mind works. And that's one of the key books, and the key person, Antonio Damasio, and his work on feelings in MIT Review and other places, in Nature magazine. How do people who have brain damage, how do they go about making decisions, avoiding risk and so forth? Very critical points. In some of my presentations, basically, I invoke his work on the affects and feelings and how they are not only bad, but also good. But sometimes when we talk of biases in human beings, we throw the good out with the bad. There's a work by very smart people out there, but we forget the good things. And I think we need to look at some of these fields with the affect, cognition, action. Humans are not just cognitive machines. They are goal-driven, purposive machines. And challenge happens basically in our systems. Machines are just intermediaries between humans. Machines are not good or bad. It's people trying to protect their own interests, looking at the world in different views, cultural. We have individual cultures and families, organizations, countries, and across the world. And the question is, how can we have the common mind share to actually look at the good of all 7 billion or so? I think those are challenges here. The final issues, if you look back at the work of the smartest people, Herbert Simon, one of the greatest guys, and AI pioneer, a Nobel laureate again. If you look back at their work, everyone was focused on the human issues and human beings. And Weiner, Anthony Weiner, in fact, he wrote a book. If you go to Cybernetics of Systems, he wrote a book titled Human Purpose, Human Beings. You know, these people were talking about technology, but lately I think we've forgotten that it's the human elements again, which you shared actually. And I think we will have better realization if we start not only start not doubting, we stop doubting every human being and start trusting every machine. What we have done, you know, we need to find a balance there. In fact, there's very smart psychologists and other people, philosophers who have mentioned this is kind of a tragedy that humans have become tools of their tools. You know, these actual quotes which are there from very, very smart people. And the question is how we can make sure that humans do not slightly blindly obey data, obey technology, and how they can have the critical analysis. That's where the educational systems, the curriculum, which you mentioned earlier, which is focused on rote memorization. How can we help them advance to create the new and not regurgitate them? They might have definition. And if we quote some of the smartest quantum scientists out there, I think Feynman is one of them. He mentioned that you can know the name of a bird in 60 different languages and still know nothing about the bird. You know, people may know 20 million definitions of quantum and they still may not have any clue about quantum. And my challenge with those many people who just know the book stuff, but those books were great. People wrote something at some point. They kind of just are stuck there. They need to interact with the real world and see what those phenomena are. And I think the real world is so fascinating, so interesting compared to any book, any course. But those help us organize structure. But the real world is most fascinating and we need to engage more with that. Thank you.
Thank you. Thank you so much, Dr. Yogi. Yeah, for sure, the human values and ethics in science and technologies is very, very important. Whatever we're going to achieve, if we're going to go, it will be used to our own doom, we don't want it for sure. That's for sure. And that's why a part of what we do also is raising awareness on technologies and the risks of technologies and the ethics of technologies. It's very, very important. Thank you so much. And I have one more question here. How will we transition to quantum communication infrastructure?
I guess I'll take that one. I guess in small steps is the answer. The way we are starting to transition to quantum communication infrastructure is some of the examples that I gave you, like we are working closely with university. So at this moment, I'm very excited to say that the barriers that existed between academia and industry are slowly breaking down, at least in the quantum world. I think it's a very give and take kind of relationship, a very symbiotic relationship, which I absolutely love. And I like seeing that mobility between the two sectors. And that is where innovation lies, between two sectors at the edge all the time. And so for quantum infrastructure, we are slowly starting to take, handshake with researchers, take their big optics labs, make them into smaller labs in industry. One thing industry does is try to accelerate the innovation of things. One thing academia does really well is delve into the tiny details that will make us trust what we are actually building. The second example I'll give you is, for example, we need some kind of quantum receivers on the ground. So we start doing that by looking at what kind of ground infrastructure we already have today. How do we make small modifications to our classical RF receivers on the ground and maybe attach some kind of a quantum receiver on there, like an optical box on there, so that we can modify the present architecture to enable it to make sure that it can also do quantum stuff. Now, it's not going to happen all overnight. All these innovations do not happen by one person or at a single moment of time. Everything happens in very, very small steps. It'll be you, me, a lot of people watching this show. It will be Yogesh, Clarice, Alethea, Hien, all of us together. And it will also happen when we understand what changes do we actually require in present day's infrastructure. It requires an understanding of classical as well as in quantum. So I don't think anyone having an understanding of only one side of the game is going to be making much of a difference. What else? Yeah, just small example, exactly how we went from computers, big computers. So when computers started, they were all like a big room. It filled up a whole room, right? And today quantum computers are exactly that size. They're filling up a whole room, but we're already talking about quantum random number generators on a chip. We are talking about quantum sensors on a chip. We are building quantum sources on a chip size scale. So, and just like how we went to mobile phones from computers and clocks and like an Apple Watch, which is this small, right? We will be going from taking that whole big quantum computer into a whole room to making something that we can, have on our palm tops maybe. And next, having that even on a tiny chip scale, which we can put in someone's body to measure some other things. So maybe Professor Claris can, add to that as well.
No, that was perfect. I would just like to, if that's possible, to hook up on what you just said, that it's needed collaboration between industry and academia and people on the ground, people in space, and also talk a little bit about and ask actually something that about which has just been mentioned about ethics and stuff. Every time I'm in a panel that discusses quantum computing, I'm trying to hear what other people think about this question, because this question bothers me deeply, in the sense that what's like and I would like to hear your answers if possible. What's like the geopolitical implications of some nations having access to quantum computing and some not? How is this going to play out in the global scale, right? Are we going to leave nations behind and all those nations will have their banks hacked? Or so tell me more. I would love to hear, because I don't know how I feel about it, and I would like to hear the experts.
I'm sure Yogesh and Alethea will have much more insights for you, but I'm going to do a start on this. I think this is a very important point that you raised, and something that I have been, thinking about as well on my side. I'm a big proponent of, handshaking already at the early stages when our technology is developing. So now that we know that something is working and we are developing these technologies, let's build consortia around the world, and let's make sure that we are making these things accessible, right, to people that we might leave behind. Because what we don't want is, we don't want a repeat of what we had done previously. We don't want a repeat of colonialism in space, right? We want everybody to go there together. We do not want to increase the inequalities that are already there on Earth by bringing fancy technology into Earth. As Yogesh was saying, machine is just a machine. It is our duty to understand how we can actually make sure these machines are everywhere in the world together. We understand what implications they would have on underrepresented demographics, what implications they have on gender, what implications they have on race. For example, when you're doing artificial intelligence, neural network training, it was important to look at which kind of sample data are you training your neural network on? Who are on the team who are doing this training sample? It cannot be all male. It cannot be all white male, straight male, right? And we figured out that it was actually leaving out a lot of demographics out, and this might cause a lot of accidents and incidences from self-driving cars for Black people, for example. And we do not want that to happen, because this is dangerous. We are having a repeat, and we are intelligent human beings, everyone who's building these things. So we should all be talking about how we do not increase those inequalities in the world. That's my perspective.
She broke up. So do you have an insight for that, Dr. Alethea?
Yeah, absolutely. I mean,
from the government side. So yeah, you tell us.
So that's a loaded question. Multiple variables. Dr. Sonali covered a lot. It's about building the ecosystem, right? And it's about having these platforms, this kind of conversations. I'm learning about Dr. Sonali, Dr. Yogesh, and Professor Claris and what they're doing. So it's building the awareness, building the platform of getting to know. But at the end of the day, also one other things that she kind of pointed out in terms of, the building of the ecosystem and everything. There are other fundamental stuff, like in terms of technology. Okay, in government, right? We have what we call the Wassenaar arrangement, which is 42 countries that come together to kind of talk about the treaties, the export controls. What can we live within each other? So when I believe Dr. Sonali talked about that in a bit, which was talking about the satellites, was, we have to talk about those treaties, the kind of in the foundational stuff up front. At the end of the day, we still have to talk about those basic policy and regulations too. It's an uncomfortable conversation that still has to happen. We trust human nature, but we also have to trust but verify, right? So, I mean, there's multiple angles that you can think of this too. But she talked about some of the social, economic part, the political side, we will have to work on the regulations, just like the WASNAR, the export controls. We still have to do all of that. We still have to consider that. So, I mean, that's, multiple things. I'm sure Dr. Yogi has more to add too.
Yeah, Dr. Yogi, do you have something to say about that? I'm sure you do.
Thank you very much. I think this is a fascinating discussion. I love all your viewpoints. In fact, I think your discussion reminded me of one of the Princeton presentations. I think it was the second presentation, which focused on ethics. And the reference was to the European Parliament. And they were basically asking, how do you make sure the issue we discussed about the trusted autonomy here, how do we make sure machines will do what you want to do and not do what you really don't want to happen, And I think question simply here is machines are machines, and there are two things here. It's a matter of design their boundaries, and those boundaries will break and can break. And we need to have some way of guiding them. And second is the adversarial issues are becoming much more prevalent now. And given the context of adversarial issues, the geopolitical environment is very critical right now. But if you observe across the whole humanity, 7 billion people, I think most people around the world, if you forget the governments for a while, and the militaries, I think those are really good people, but they act at the behest of governments, And I think military people from different countries respect each other more and are more sympathetic to each other. That's what my perception is, belief is, because they understand that they are all fighting for the causes, the beliefs, what they are told to. They are told to obey the commands, and they have to, and those issues are there. But the challenge, I think, goes back to the issue of control, which we studied in depth a long time ago. And in control, the primary issue which comes to is there's two different things which at human level, if you look at machines as emulating humans, one is what's motivation, second is commitment. We build the early models of these particular things which have been applied by NASA among other organizations. But if you look at the commitment, is it, and social influence is the primary driver. There's a lot of work coming from Harvard and other psychologists. But if you look at influence is a big thing right now. Is it compliance? Is it identification? Or is it internalization? These are three constructs, actual constructs, which have been studied. And actually, you will find if we internalize things, we do it because we love it, we value it, Compliance, yeah, we'll do it if we care to, if we have to. But the challenge right now with the global ethics regulation, which I think Dr. Alethea pointed out, as well as Dr. Sonali, the regulation, no regulation there. The biggest challenge is, I think there are two areas here. We have regulations in many areas, even in the space and satellites and adversarial uses of space and other things. But the challenge is, how do you ensure compliance? And how do you, one big question which I've raised for our very nice people in the JAIC, which is Joint Artificial Intelligence Center. And there's a fascinating person they had for ethics, to head ethics. The question I'm asking simply here is, how do you live by ethics with an adversary who doesn't care about ethics or laws? Now, those are very critical questions. Now, I'm not saying that people good and bad, but that's the way certain parties, certain things operate. These happen not only at country or world level. Even in specific organizations, you've seen things happen. In Silicon Valley, there are a lot of case studies, adversarial issues against specifically women in Silicon Valley, which have been brought to light. The issue is we are humans. And sometimes we say these are kind of country, political, religion. No. I think we are humans. Therefore, we need to find the common ground, the shared goal, the congruence, regardless of our differences. The differences are good and bad. But is it possible to focus on what's good and make it great rather than the bad, which kind of takes us all down? And I was sharing with one of the people at Pentagon from military. I think I was trying to share a quotation somewhere I read a long time ago. Either we can hang together or we will be hung separately. And I think if we trust technologies too much and forget about the humans, I think that's what the biggest risk in this atomic clock running near the midnight, that's what we are seeing is the big risk right now. And I think all of us, as I think Dr. Sonali mentioned, we have to participate and help raise awareness. Thank you so much. I appreciate it.
Thank you. Actually, I would add something coming from international law background, and this is how I enter into the quantum. The quantum is and sustainable development background is how it will help us to move forward and achieve the sustainable development goals and help us to make our a new evolution. Before we were in the space race, now we are in the quantum race. So the thing is like, how can we ensure a certain governance while we're not ensuring the governance with the space activity, commercial activities? So this is the thing, is like, how can we move forward in a ecosystem that it is based on national interest, of race between nations, Now the race is between super technological powers. We have Google, we have IBM, and so on. So the thing is like, how can all this be governed in a way nations and national security point of view through international public law and treaties and agreements? And the other one, how can we govern on a way of private activities, which is based on contractual basis and based on national laws and agreements and so on. And here, I think scientists, as you are, you have the lead for that, because coming from different people that they are into laws and international law background and so on. We do not master what you do. So this is your domain to go raise awareness and really advocate for what needs to be done. And we are there following you, and that's what we are doing, raising awareness. To wrap up this, I have the last question, and this last question is about job opportunities. Actually, the question is like, we know that the quantum race is already underway for the second revolution of quantum. And governments and private investors all around the world are pouring billions and billions of dollars into quantum research and development. This would take time for ROI, for return on investment. The question is like, how can this be commercialized? How can it scale up? And how can open opportunities to our mentees that they are watching today, and they are so fascinated about it, and they want to enter into this nice economy that it will be emerging later, not now.
I can say 2 words about the trainees and the workforce.
Sure.
There is an incredible need for people from super diverse background in the quantum sciences, and it's been clear now that we need people from electrical engineering, physics, chemistry, computer science, right? Who am I forgetting here? So many backgrounds are actually needed to ensure this boom of quantum, right? I think quantum is being democratized, and the value of, as Sonali mentioned, diversity not only in terms of gender and race and religion, but also in terms of areas of expertise. So I think that the trainees, almost regardless your original background, I think you might be able to navigate and to enter the quantum force, and a smart quantum workforce is sorely needed. There are many, there are many master programs around the world that are being developed to train people with diverse backgrounds to enter the quantum force relatively fast. And also, there's also the more common route of obtaining a PhD before joining the quantum force too. But it's, I believe it's going, the like workforce is going to explode very soon. It's already exploded.
Yeah, I'll follow Professor Claris into just giving a personal example. So on a day-to-day basis, who do I talk to? Basically, my background is coming from quantum physics and quantum gravity. So I did a lot of particle physics and quantum gravity before I went into quantum technologies. On a daily basis, what does the quantum workforce look like for me? I talk to optical engineers. I talk to researchers like physicists, chemistry researchers, researchers in machine learning and artificial intelligence. But this is only the research side. Next, I talk to classical engineers, RF engineers. I talk to electronic engineers, embedded systems engineers. Next, I talk to HR people, secretaries, project managers, people who communicate what does quantum mean to the bigger part of the world. I talk to marketing companies who are doing space marketing, quantum marketing. They're trying to make the workforce accessible to more people. I talk to people who are building up curriculums for school students, for undergraduates and graduates and PhD students. I talk to the government who are trying to come up with what sort of opportunities should we make available. And then I talk to companies who are trying to figure out what kind of products are more accessible. So these companies can start from mechanical engineers, materials manufacturers. They are basically workshops, people who do drilling and machining of the parts that we ask them to do. Then there are people who are making clocks. There are people who are, there are people who are running thermal chambers, who are, sales forces on those teams. So basically everyone, right? There is nobody that has been left out. And if I left anyone out, jump in and join us because we need you. That's the answer.
So to pile on to that, you guys made excellent points in the workforce from the government side. I mean, these are all dual use technologies. So we can't do this without industry. We can't do this without academia. We can't do this without anyone. So the continuous dialogue collaboration is what makes us thrive. From the government side, at least in Air Force side, we have innovation hubs. We're opening up, we're opening up. Come in, do business with us. We have the small business innovation research funds. We're doing lots of things happening. So we can't do this alone. At the end of the day, I think we all agree, humans, we all have to work, take away the technologies and everything. We have to work together. So I think from our standpoint is we still have to keep having this dialogue, open up collaboration. And, with our hubs, this is a way for us to start harnessing these dual use technologies. So 100% agree.
Oh, I shouldn't forget to pass the mic in this case, because I have been talking to some very interesting 16-year-olds who are making all the ripples. So they have, I think, some of the founders of Space for All who are making space education accessible to school students, and I'm sure there's like thousands of amazing 16-year-olds and less, younger generation who are doing amazing work. So any age, there is no age that you could you could start joining the quantum workforce, to be honest. So don't let any obstacles tell you that you can't do it, is the answer.
Sure, I think that's fascinating. I think just extending on that, if we look at quantum computing, what I find very fascinating, some of these big companies which are getting involved in a very big way with the help of government grants, we are seeing a lot of involvement by Defense Department, which wants to encourage entrepreneurship. You can follow Alethia's feed on LinkedIn, or you can follow my feed. We are marking a lot of that for the security side, and a lot of entrepreneurship in a very big way from the technology plus security. From the other standpoint, the quantum computing. Actual education, if you want to follow my feed, I've been marking some of the actual courses which are being offered free of course by big companies like IBM. In fact, just to make sure, a lot of work which I've been doing for the last 8-10 years and presenting on quantum, I actually get my hands wet with the actual programming. When I came to know of IBM Qiskit camp, I said, okay, let me see what it is. I went from two perspectives. As a professor who wants to learn and teach, how do we actually teach programming? I programmed in more than 24 languages. I don't remember any of them. To me, it's all pattern processing. I was trying to think, how do we look at quantum in a different way? And secondly, it was from actually how we can apply this programming and what's the state of technologies. It's still evolving. It's tons of languages. But the thing is that this community, they opened to about, I believe, 200 people or so who are going to participate. At the end, they had 5,000 people worldwide. And I was trying to understand how they can create this big community. And we found a whole lot of diversity of people from high school, college, and whatever, and very senior people. And I think the fascinating perspective you can have by immersion learning, as I call it, being a part of those, you can see a whole lot that all of us can learn from all people of all demographics, and those are some communities of interest. This being one here, what TN is running, this is a fascinating community. It's intersection across various communities. The space community, defense community, the biological community, which I find very fascinating, biological, electromagnetic. That's a fascinating area which I have yet to know more about. And the technical side of thing, what I think Sonali, you mentioned, is beautiful. Love it, because I've been reading a whole lot about it, never built this satellite, but I would love to see or understand how we can do that. But I think this synthesis is great. Thank you so much for this opportunity. Would love to continue the conversations after this. Thank you.
Thank you, everyone. Thank you for this dynamic, enthusiastic, and passionate expertise that you brought to this very complex theme. I know Alethia has to shoot off to the airport, so I'll make the closing very quick and fast. So thank you everyone for your sharing your expertise, I personally would have to review this show several times to understand. I know you try to make everything very simple. We learned about ethical AI, human values and adversity. Let's continue this conversation. The recordings will be sent out along with the presenter slides. So I thank everyone for your participation today, and stay safe and stay well. Everyone will have the next show next week will be about space architecture. How does analog space architecture can influence the way we live in space? So stay tuned and register on time, and we're looking forward to see you next week again.